you what its role is too. And then the second organelle that I'll tell you about muscle cells are these here, these ropes here. This is intracellular organelle, and these are called myofibrils. And these are made up of this famous actin and myosin proteins that actually do contraction. And maybe you've gone over the sliding muscle theory of contraction already. But my hope is in my class you always really understand it clearly. Okay, so that's what we're going to focus on. And of course, you know me, rather than just having you stare at the PowerPoint projection, I like to have you draw it. So there you are. You got today, yeah. Let's draw it. Good there. Still there? Okay. I think I got enough detail here. I can turn this on. Okay, so what we have here is this synapse looks hopefully just like the synapse that we've drawn already in class. So everything here works pretty much the same. This nerve here looks the same as the nerve you've seen before, but this is specifically a nerve that goes to and synapses on a muscle, skeletal muscle cell. So those are specifically called motor neurons. So this is a motor neuron. Motor neuron. But other than that, it works just like the axons and synaptoterminal cycles that we've done in class already. And this whole cell, this is a single cell right here. This is a muscle fiber cell with all the stuff that's inside it. So I'm going to label that. The muscle fiber. And I just want to remind you that this is actually a single cell. I'll just tell you that it's a cell so you don't forget. Now I got to start naming all the parts. So one thing that's kind of complicated about this is there's a lot of vocabulary, but other than that, the physiology is not that complicated. So first of all, the motor neuron is the same, works the same as the ones we've done before. synaptic vesicles, voltage-gated sodium channels, voltage-gated calcium channels. You know about that already. You even know about the neurotransmitter that's released from the motor neuron. It's the same one. It's acetylcholine, the same one we've worked with before. So motor neurons, they work with, there you go, I'll mark that, ACH for short. Acetylcholine, they use that. Okay. Now, that's the easy part. Now, let's do the muscle fiber cell. Remember I told you that the cell membrane has a specific name when it's a muscle cell? And so the name is the sarcolemma. S-A-R-C-O-L-E-M. Okay, that's the cell membrane. And there's another specificity about muscle cells is that they have this infolding of the sarcolemma. You can call it an invagination, frequently along the cell membrane. And what it does is it carries the action potential deep into the inside of the cell. So it has an important function, and therefore in the name it's called the T-tubule. The T-tubules are a deep infolding of the sarcolemma inside of the cell. On my drawing, I've got two T-tubules right there. Just two of them. Okay. Next, we have in the inside of the cell, I've drawn here. This is this intracellular vesicle. I'm sorry. This is this intracellular organelle that is filled full of calcium ions, and its name was sarcoplasmic reticulum. See, as I told you, the complicated thing about this is there's a fair amount of vocabulary. So this is the sarcoplasmic reticulum. U-L-U-M. The sarcoplasmic reticulum. It's like endoplasmic reticulum, but specialized for skeletal muscle cells. And you may have noticed the sarcoplasmic reticulum, it has a calcium primary active transport pumps on its cell membrane, and it pumps calcium from the cytoplasm into the sarcoplasmic reticulum. That's its job. It's a bag that's stuffed full of calcium. And I think I have marked on your sheet already. Therefore, the calcium concentration is very high inside the sarcoplasmic reticulum, but in the cytoplasm, calcium is very low. Okay. Yeah, this sarcoplasmic reticulum, this intracellular organelle, it's basically a bag full of calcium. And the way that it's stuffed full of calcium is that it has on its membrane, it has several calcium ATPase pumps, primary active transporters, that pump calcium from the cytoplasm. This is where my finger is. This is cytoplasm into the sarcoplasmic reticulum. So it's very high calcium on the inside and then low calcium in the cytoplasm. Here also, you see here is cytoplasm also. Here's cytoplasm also. This is just a sarcoplasmic reticulum there. Now, just to make sure that calcium is very low in the cytoplasm, you also have some more calcium active transporters. Here's a primary active transporter for calcium right there on the sarcoplasmic reticulum. Make sure that it's very low in the cytoplasm. And here's you recognize your old friend, the secondary active transporter. Allows sodium to diffuse in, and that releases energy that actively transports calcium out. So you've seen those two before. They help maintain calcium levels very low on the inside. Okay. Now, here's some more terminologies. There's another channel located on the sarcoplasmic reticulum. I have one there and one there. And they have an unusually long name. So I'm going to label it right there. Okay? This is the channel on the sarcoplasmic reticulum. And I'm going to call it the DHP/R channel. Kind of a weird name. And the reason is because it has a long name and it's a pain in the neck to remember the whole name. It stands for dihydropyridine/ryanidine channel. Dihydropyridine/ryanidine. So I just shortened it to DHP/R. My next slide on the PowerPoint spells it out for you so you can see how you spell dihydropyridine/ryanidine. If you have to write this on my exam, on the final exam, you can write just DHP/R. That's fine. You agree? Yeah. Okay, good. Okay, well, we're getting somewhere. Not quite done yet, though. I told you there's two intracellular organelles that you got to worry about: sarcoplasmic reticulum, and then here's the other one. This is the myofibril. Okay, so I'm going to label that. There it goes. Let's see. Myofibril. And now the myofibril itself is made up of repeating units. Each unit, I've just drawn one unit right here. Each unit is called a sarcomere. So here's one sarcomere. That's spelled S-A-R-C-O-M-E-R-E. Sarcomere. Okay? This is where all the contraction happens. I apologize, the writing is getting rather small here, and you can get into all sorts of details about sarcomeres, but I'll keep it simple. The sarcomere is basically made up of two Z lines. The Z line is a protein that goes zigzag, zigzag, zigzag. So that's the Z, that's called the Z line. And this is also the Z line over here. And then attached to the Z line are thin filaments, famously known as actin. And then thick filaments in the center, famously known as myosin in the center. Okay. Now, you probably can't see what I'm pointing the arrow to, so I tell you what, I'm going to write a portion of the sarcomere over here. I got some room there. So I'm going to give you a big Z line. Make it bigger. Get that a little bit bigger. Boom, 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 boom. There's our Z line. And here's the actin, kind of looks like this. There's more realistic to what actin looks like, and the myosin looks like this. It is thicker. And it's got these heads that come off like this. That's what they really look like. So that's the Z line. This is actin. And this is myosin. Myosin is this thick protein in the center. It's got these heads that come out. Actin is this thinner protein that's connected to the Z line. All of these are proteins. They're all proteins. Okay. I've labeled everything except for one thing, which is the acetylcholine receptor here. Remember I told you before that the acetylcholine receptor of the parasympathetic nervous system is called the cholinergic muscarinic receptor? You may remember that. I'll remind you, don't worry. This is an acetylcholine receptor here, but it's a different one. The acetylcholine receptor of skeletal muscle cells has a different name. And that is called the cholinergic. That means that it binds acetylcholine, and it's called nicotinic receptor. The nicotinic receptor, specific for skeletal muscle cells. Yeah, I got all of it. Beware of some terminology here. Did you notice that there is the sarcolemma, sarcoplasmic reticulum, sarcomere? You notice those three? They all kind of sound the same, right? So they're all different, so you got to keep those straight out of your heads. Just like that one test question I gave you in your midterm, one about glycolysis, gluconeogenesis, glycogenesis. Remember that? And I put it in 7-point typeface to make it even harder.
Oh yeah.
Remember that? Yeah. That was my idea of a joke actually. It was really small. Yeah, you still like the joke, right?
I get it, so it'll be hard to read.
Yeah, that was my mean joke on you. Might do that with this. Who knows? Depends on my mood. But fine. Okay. Now, geez, we did all this anatomy, but I haven't told you what happens yet. So you ready to see how it works? Okay. Let's do it. Start at the top. We have an okay. So my brain is going to tell my finger to do this. Okay, that's a skeletal muscle right there. So my brain is going to send an action potential from my motor cortex down along my arm all the way to my muscle right there. And so this is action potential coming down, the motor neuron. The action potential is everything you know about already. Longitudinal current, transverse current, capacitance current, voltage gated sodium channels, voltage gated potassium channels. All that's going on. We get to the center terminal. You open voltage gated calcium channel, calcium fuses in. Calcium is the messenger that tells the synaptic vesicles to move forward, to bind with the membrane and go through exocytosis. Acetylcholine diffuses across the cleft. This is all reviewed, by the way, right? And now here's where we get to the new stuff. Acetylcholine binds with the cholinergic nicotinic receptor. Okay. When it does that, it causes this channel to open up causes the receptor to open a channel for sodium. Opens the channel for sodium. So sodium, of course, is high on the outside and low on the inside, and sodium diffuses in. Okay. Sodium diffusing in causes depolarization, right? Depolarization. Now, this muscle cell works just like a neuron, so it's positive on the outside, and it's negative on the inside. And it also works just like a neuron in that I didn't draw it. You can draw it if you want. But there are voltage-gated sodium channels and voltage-gated potassium channels on this membrane. Okay, you got it? They're there. Which means that when I depolarize enough with sodium, it reaches action potential along the sarcolemma, just like a neuron. And the action potential spreads along the sarcolemma. The action potential goes down into the inside of the cell via the T-tubule, And when the action potential reaches the dihydropyridine ranitidine channel, it causes it to open. And once it is open, now calcium can diffuse from the sarcoplasmic reticulum into the cytoplasm. So there it is. And here on the other side too. There it is going into the cytoplasm. Okay. Calcium diffuses in the cytoplasm and it makes it all the way to the sarcomere. And then calcium is the signal that tells the sarcomere to constrict. And that's the whole process right there. What do you think of that? Of course, it's not the whole story. I didn't tell you about how the constriction actually works yet, right? Now, let me tell you one thing. I just told you how I constrict my arm, right? But just as for skeletal muscle, just as important as constriction is relaxation. For example, when I constrict my bicep, my tricep has to relax, right? And vice versa. So, muscle relaxation is everything I just told you, except everything goes in reverse. So now I'm going to have to put it all in reverse. Okay, I want my muscle to relax. You stop firing action potentials. You stop releasing acetylcholine, and then you get acetylcholine out of the cleft. Remember the three mechanisms? How to get it out of the cleft? Diffusion, reuptake, and enzymatic degradation. Same three mechanisms. Then the cholinergic channels close because they're no longer binding acetylcholine. They close. Sodium no longer comes in. No more action potentials. Dihydropyridine ranitidine closes. And then, as soon as it closes, you pump calcium out of the cytoplasm really fast. You pump it out there, you pump it out there, you pump it out there, and almost instantaneously, calcium levels go near zero in the cytoplasm. And when they go near zero, then the sarcomere relaxes. So there you go. Muscle relaxation is just as important as muscle contraction for muscles to work properly. Yeah, question.
So when the calcium diffuses into the sarcomere, it causes constriction,
Yeah,
and then when there is none, it causes relaxation.
exactly.
Okay.
Yeah. I haven't shown you how it works yet, but of course I'm just about to. Any other questions?
Can we go through the whole thing one more time, please?
Sure.
After the calcium diffusing inside.
How about starting with acetylcholine binding with its receptor?
Yes.
Is that a good place to start?
Mhm.
Okay. Y'all ready? Acetylcholine binds with its receptor, which is the cholinergic nicotinic receptor. That opens the channel for sodium. That channel opens, sodium diffuses to the inside of the cell, depolarizes the inside of the cell, causes the membrane to reach threshold and have action potential. And I'll repeat, there are voltage-gated sodium channels, voltage-gated potassium channels here, but I did not draw them in this example. I thought there was too much stuff already, but they're there. The action potential goes down the sarcolemma, and it is actually the action potential at the dihydropyridine ranitidine channel that causes it to open. You see, the action potential causes it to go through a conformational change. It opens, and then calcium can diffuse through it from the sarcoplasmic reticulum into the cytoplasm, and it immediately diffuses to the sarcomeres and causes them to constrict. Okay, there you are. So let's take a look at, let's see how you spell dihydropyridine.
Excuse me, Professor.
Yeah.
How does the calcium get into get into you know the calcium sac, the sarcoplasmic reticulum.
Well, I'll show you. It's actually loaded full of calcium ATPases. Right there, see that? Yeah, it's loaded that they take it out of the cytoplasm and put it into the cytoplasm. See the arrow going in?
Okay.
Yeah. So they're always pumping it in, always. Yeah.
So are they also? How did they get through this part?
The calcium?
Yeah.
This is all cytoplasm here. So the only place you have high calcium is inside the sarcoplasm.
Okay.
Yeah.
Okay.
That's the only place.
Okay, got it. Thank you.
This is what it actually looks like, and that's actually how it's spelled. So there you go. Dihydropyridine ryanidine. That's why I wrote DHP off. Okay? That's a lot easier. This is what it looks like. This is actually the T-tubule. This is actually your sarcoplasmic reticulum membrane. So that when the action potential comes down the T-tubule, it causes this to go through a conformational change, such that it actually kind of pushes this open, this channel, and then calcium can diffuse from the sarcoplasmic reticulum into the cell, to the sarcomere. So that's what it actually looks like. I drew like a little itty bitty one there in your drawing there. All right. Here's something just for fun. See that guy there, the one standing up? His name is Gregorio Valdez, this guy here. He graduated from here back in the 90s. When I first was hired in 1994, he was an undergraduate student in biology. He's from the Dominican Republic. And when I met him, he didn't really speak English yet. And he drove gypsy cabs in the Bronx to pay for his tuition. And that's when I met him back in the 90s. So he got his biology degree here. He learned English really fast. And he got involved in some research program here at the college and decided like that. And so he went on and got a PhD at Stony Brook. And after that, he went to Harvard. Well, you know, if you're a medical doctor, you have to do a residency for a few years. If you get a PhD, you have to do what's called a postdoctoral fellowship for a few years. It's the same thing as a residency. You do research underneath a famous professor for several years, and you have to do it if you want to get a good job. So he did a postdoctoral fellowship at Harvard with a fairly famous person for 6 years, actually. And he became an expert at this motor neuron synapsing onto the skeletal muscle cell. It's called the motor implant. He became like a real expert on that over those 6 years. And finally, he got hired at Brown University up in Providence, Rhode Island, which you know is a pretty good school. And he's a big deal professor with a big lab and millions of dollars of grants, several graduate students, so he's doing good. Isn't that cool? It's always good to see Lincoln College students making it big, especially the Dominican ones. And he's still a friend of mine, too. By the way, I was getting so excited about this, I forgot to mention that this and that you already drew, but you just didn't know it. Remember this slide that we did? Where you had an axon and like these little buds and then the skeletal muscle fibers. Remember drawing that? Sort of? Mm-hmm. That's this, you see. This is the axon, that's the motor neuron. That's the synaptic terminal. That's this, you see? That's the synaptic terminal. It's just dyed really dark so you can see it really well. And then that's the muscle fiber cell right there. That would be all of this. Now, in your slides that you did in class, these were they were very faint, so you couldn't see them very well. It was kind of like light pink. But you actually drew the actual thing. So, and this synapse is what Professor Valdez is like a world expert at. All right, let's get get past Dr. Valdez. Let's see. So, okay. Get this drawing out. We don't have one of these. Get this one out now. It'll make it easier what I'm about to talk about, okay? Remember I had you draw, on your drawing, I had you draw a Z line. This was actin, this thin filament. This was myosin. Myosin was the three heads there. I'm going to show you the actual detail of it right now. So here's actin here. This is the thin filament. Actin is actually complicated. Actin is actually made up of three separate proteins. They're listed on the top of your sheet right there. Three separate proteins. Myosin is thick and it has these three heads. And there's the three heads of myosin. You see on the top of your drawing, see that? There's myosin, there's actin. So actin is complicated, it's made up of three separate proteins, but I've labeled them for you. Let's take a look at what they do. Do you see on your drawing that actin is made up of what's called F-actin and then tropomyosin? It's not exactly the same yet. How similar is it though? It is almost the same, yeah. Yours is better than this. F-actin, tropomyosin, and troponin is this small molecule like made up of three subunits right there. And it looks like it's binding calcium up on the top there. So each of those three plays a role that I have to explain to you one at a time. Okay, so here we go. First of all, F-actin. I want you to think of F-actin as two strings of pearls that you hold together and then you give it a twist. Okay? And you see the double-stranded pearls that are twisted into a double helix, like that on your drawing? That's F-actin. That's a type of protein. Okay? Now, each pearl is a protein in itself, so there's one of them right there. Each pearl itself is called G-actin. You can write that in if you want. Each pearl is called G-actin. G stands for globular. It means that it's in the shape of a globule or a sphere. F-actin stands for filamentous or filament-like because it forms these filaments. So again, F-actin is made up of many G-actins. Think of F-actin as a double-stranded pearls that are twisted into a double helix. Each pearl is G-actin. And do you see that each of your G-actin molecules, each pearl has a black dot? I think yours do, don't they? Yeah, they do. That's because I got it. Each G-actin molecule has a black dot. And you should label that as, that's important because the black dot is the binding site for myosin. That's where myosin likes to bind. Okay, so that's F-actin. That's the hardest one. By the way, you'll notice that I gave you like some sort of definitions on the bottom. I should be saying pretty much the same thing as the definition, but they're there in case you miss anything, okay? In case you miss anything. Okay, so that's F-actin. Now, what about tropomyosin? Tropomyosin is this dark cord. I like to say sometimes it looks like black licorice. And it's two strands that look like they're wound around F-actin, also in a double helix. That's tropomyosin. This black licorice, two of them are wound around F-actin. Okay? That's tropomyosin. Now, tropomyosin's job is, as you can see right here where my finger is, it puts itself in a conformation where it blocks the binding site for myosin. So myosin wants to bind, but it can't because it's blocked by tropomyosin. See that? It's blocking it. But that's when there's no calcium available. But what happens though is when calcium is available, if you look on the bottom here, tropomyosin, it tightens up and it kind of fits into the grooves of F-actin and uncovers the binding site for myosin, and now myosin can bind it back. So that's the job of tropomyosin, is it covers and uncovers the binding site for myosin. So that's protein number 2. Now you get protein number 3. Protein number 3, here you go, is troponin. That's this trimer right there. This is this 3-unit protein. Troponin there, and it's physically attached to tropomyosin right there. They're physically attached, okay? Troponin. Now troponin's job is, it's a protein. Its job is it binds calcium. It's a binding site for calcium. So when troponin binds calcium, it tells tropomyosin to move off of the binding site for myosin. I'll repeat that. They work together as a team. You see, troponin and tropomyosin, they work together as a team. So again, when there's no calcium, troponin, tropomyosin are blocking the binding site for myosin. But when there is calcium, troponin binds calcium, and then they both go through a conformational change such that troponin and tropomyosin, they move off the binding site for myosin. Now myosin can bind. So there you go. I apologize. Actin itself is complicated because it's made up of 3 separate proteins, but each of them has their own role. Okay. Any questions about that? Okay, so that means we can get on to the last slide of the day, and it also means that you can answer your homework questions, or your last questions. So let's have you get this one up. That's such a nice drawing, it's a shame to erase, right? Maybe only in my mind. Okay, someone have one of these? It's got 5 or 6 steps on it. Where'd it go? There it is. 5 steps. I hope you recognize, at least in, you can kind of see what's going on here. I have my F-actin as a beautiful purple. Looks like my, let me lower it down here just for a little bit. That's good enough, yeah. So you're drawing here, of course you don't have color, but you can see it easily here. F-actin, the double-stranded pearls, is in a nice purple. Tropomyosin is a darker purple, right there. There it is, tropomyosin. And then for some reason, troponin is a bright cherry red. And then the calcium ion that's binding to troponin is a nice green color there. And then finally, the myosin with the myosin heads is kind of a lime green, very colorful. Sorry, we don't have color, but you see all the parts though, right? Okay, so that's the way this one works. So it's all labeled just like I just showed you. And I think the easiest way to do this is if you break it down into numbers. So at the very top, I'm going to call this number 1. I'm going to call this number 2, number 3. Number 4, and the last one on the bottom is number 5. And there's a lot going on here, but if you just kind of make a note about what's going on at each step, it makes it easier. Well, by the way, if you look at number 5, you may notice that it's just about the same as number 1 on your drawing, which is in fact true, because this is a cycle. that it goes through this cycle continuously while it's constricting. So you can have another line that goes like that. Meaning it's a cycle. It cycles through 1 through 5 over and over and over again while you're constricting. Okay, so let's start at the top. Number 1, just a couple notes about what's actually going on here. Number 1, I'll make a note to myself. I'll say calcium is present. Okay? Calcium is present, and in fact, when calcium is present, calcium binds to troponin, which is it's bound to it on your sheet there, right? And also, when calcium is present, it binds to troponin. Troponin and tropomyosin move off the binding site for myosin. So I'll say that actin is uncovered. It is uncovered. And you can actually see in your drawing there that there's the beautiful binding site for myosin right there. Tropomyosin's off of it. Myosin can bind to it, and which of course that's what it will do. I don't like it like that. Let me do it like this. How about like this? 1, 2. I don't like it like that either. How about
Maybe A, B, C.
A and B? Okay? Okay, 2. Hey, what's going on number 2? Well, the binding site is uncovered, so there it is, myosin binds actin. That's what it does. That's what happens in number 2. Very simple. Okay. See right there? Here it's not, there it's not. Okay. Now, I want you now to pay attention to the myosin head, and I want you to pay attention to the angle that it's at, because that's important. It's a protein, it's in a particular conformation. Do you notice that the myosin head is at a conformation or an angle like that, right? Step number 2, it's also at this angle, like that. Okay? So make a note of that to yourself. If you otherwise wouldn't maybe notice. Yeah, you see what's called, this is called the myosin head region. It's actually at that angle on your sheet. But you can call that 45, something like that, and pretty close to it. Okay, number 3 is where all the action happens. Looks like, obviously, right? Myosin when myosin binds actin, that action of binding causes myosin to go through a conformational change. In other words, right when it binds it, boom, that causes myosin automatically to go from this conformation to that conformation. And let's look at the angle of the myosin now. Okay? It's gone that way, right? And by doing that, since myosin is attached to actin, as myosin goes from there to there, it's pulling actin in, obviously, to your left. So it's actually forcing actin to move in that direction by going like that. So myosin goes through a conformational change. And this is actual, that's what muscle contraction is that step right there. So I'll say contraction. That's contraction right there.
So you said like the head, what happened when the myosin head changes, that causes the actin to move to the left.
Yeah, You see, look on back on step 2, myosin's like this. I'm myosin. I'm bound to actin. I'm stuck to actin, actually. When I bind to it, it causes me, the myosin head, to go boom. And since I'm attached to actin, I'm pushing it that way. Yeah. Okay, there's a second thing that happens in step 3. You may or may not have noticed that the myosin head has adenosine diphosphate attached to it. See that now? ADP. When myosin goes through its conformational change, which is contraction, that also causes ADP to release. You can see it right there. It gets released. So that also happens in step 3. Is ADP, and formally you should say ADP, adenosine diphosphate, plus inorganic phosphate. That's how they say it, right? ADP plus P. I'll skip that. It detaches from myosin. So those two things happen in step 3, right? Now we've contracted. Okay, what happens in step 4? Well, a couple things. Look on step 4 here, and notice that there's a brand new ATP attached to myosin. See that? So myosin binds ATP. A brand new ATP. Okay. Your skeletal muscle cell is stuffed full of mitochondria making ATP all the time, so you always got a bunch of ATP available. And importantly, when myosin binds ATP, it allows the myosin head to detach. You see how in step 4 it's detached now? Only when you bind ATP can you detach. So A, B, myosin detaches from the actin filament. And you see, A causes B. See, the binding of ATP causes detachment. So those two are connected to each other. Okay, well, we're almost done. Yeah.
Doesn't A cause B also in step 3?
Probably. Let me see. Yeah, you're right. So I might as well be consistent within myself. You're absolutely right. Okay, step number 5 finally is, let's see what's happening here. Keep track of the myosin conformation. Myosin is still like this, right? Myosin is still like that, right? In step 4. Now in step 5, we break down ATP into adenosine diphosphate. And whenever you break ATP into ADP, that releases energy. And that energy is going to be used to set the myosin head back to its original conformation. Notice that myosin is back like this now. So this A causes B again. This sets myosin back to, I'll say, ready. The ready part. Ready meaning that it's ready to have another contraction. Yeah.
Is a muscle relaxation happening at step 5 or no?
This is all continuous contraction going
Okay.
on. Yeah. Yeah. Now, if you look at step 5, I mentioned this before, but I'll say it again. Step 5, myosin's back at the right position. Step 5 is pretty much the same as step 1. You see, myosin's back at ready, and myosin is not bound active yet. So step 5 is pretty much the same as step 1. And then you're going to go through step 1 through 5 again, and again, and again, and again, and again, until you relax. That's how it works. the myosin head where it's ready, it's like this, and when it goes through contraction, it goes like that. Okay. You can think of it as like an old-fashioned like Nerf gun or any spring-loaded gun where you pull the spring back and it's ready to fire. That's when it's split ATP and ADP. Now it's got tension on the spring, it's ready to go. You pull the trigger, boom, and now the spring is loose. It can't do anything. Now you have to attach a new ATP to pull the spring back again. You can think of it as like an old-fashioned spring-like gun. That's really how it works. And this conformation is under tension. It wants to go that way. And this conformation is already fired and it's kind of loose. Can't really do anything. It has to be pulled back. That's one way to think about it. All right. I just got 2 questions to ask you, and then we'll take our break. Question number 1 is, what steps can you not go through if you have no calcium available? In other words, would you get stuck between steps 1 and 2, 2 and 3, 3 and 4, 4 and 5? If you had no calcium, what steps could you not go through with no calcium?
You can't start? You can't start?
You can't start. You wouldn't go through any of them.
Could you be at step 1? You could be, right? Myosin sitting there, actin sitting there. But no calcium is available. That means that troponin and tropomyosin are covering the binding site for myosin, right? With no calcium. And that means that myosin could not attach to actin in step 2 if there's no calcium. So, in other words, step 1 to step 2, you couldn't do it. That's where you're blocked. In other words, myosin cannot attach to actin because the binding site for myosin is blocked. And that of course, no calcium, that's muscle relaxation. None of this can happen if the binding site's blocked. Question number 2 for you is, what if you run out of ATP? Which 2 steps would you get stuck between? You run out of ATP.
You
Which
can't
steps
press
would you
forward.
get stuck between? Then the question is, what does ATP do in this whole scheme here? Detaches, yeah. ATP binds to myosin, so ADT allows myosin to detach. So you wouldn't be able to go from step 3 to step 4 if you agree, right? Step 4 is detachment. So there you get, that's where you get stuck. Okay? You wouldn't be able to detach. You wouldn't be able to go from 3 to 4 if you run out of ATP. All right. There's a couple questions I'd like to ask you because it kind of asks you to really understand what's going on here. And here's kind of an interesting and slightly gruesome fact, is that when a human body or any body dies, about 1 to 2 hours after death, the cells run out of ATP completely. The muscle cells, because they're dead, no more cellular machinery. And when the muscle cells run out of ATP, you see you get stuck at step number 3. Myosin stays stuck to actin permanently. It takes ATP to unblock, to detach it, right? So about 2 hours after death, whatever position you were in when you died, laying in bed, your muscles get absolutely stuck in that position, and that's called rigor mortis, and that's the cause of it. You all heard about that, right? You heard about it, and I've heard you understood the mechanism. So again, rigor mortis is the muscles become absolutely rigid about an hour or 2 after death, and it's because the muscle cells run out of ATP, actin can't detach from myosin, so you get stuck in that whatever position you're in. Rigor mortis, about 2 hours after death. Interestingly, a girl was in my class, and she works at the vet clinic, and she said that sometimes their animal, their pet, their dog or cat dies in the clinic, and the owner wants to come and see them one last time. And sometimes they die in a really strange position. And so before the owner comes, they have to like grab the limbs and go crack, crack, crack to kind of put them into a normal position because they're rigor mortis. So there you go. Okay, let's take a break, and then we'll the lab extraction of your data is very easy. Very easy. So you're almost done tonight.